Hello everyone, welcome to Linear Model. It's me again, Sarini Abdullah. So for this session, we will learn about how to assess the usefulness of a model. To do that assessment, we have to test our hypothesis. We have to set up a hypothesis to be tested, and then to make a decision about that hypothesis, of course, we need to do some calculation. We need to produce a metric that is called the test statistics, and in the end we should make a conclusion whether our hypothesis is rejected or not based on the resulting test statistics that we calculated. So consider this model. Okay, we have our simple linear model. When is the model said to be useful? So let's see this illustration. Okay, let's say we have this data, and I will just replicate the scatter plot of the data. Let's say for the first graph, we want to tell a story about yi, but on the first graph, we don't have anything to help us tell the story about yi. In that case, an obvious thing to do is to represent yi by its center value. That is the mean of yi. That is given by, let's say it's given by this brown line here. While on the right side, let's say we have another information that will help us describe yi better. That is given by x. And so, how we explain yi is through this blue line here. So, let's consider our first line, the brown line. Let's say this line still represented by this equation, that is yi given by beta naught plus beta 1 xi plus the epsilon I. Okay, but then we are not using the information on xi. How do we know that? So let's say here for x equals something here between 5 and 10, then yi is given by this value. We change the value of xi, we still get the same y value. Change the value of xi, we still get the same y value. In this case, the existence of xi in here is not useful because whatever the value of the xi, the value of yi is exactly the same. It's just a constant. So in that case, we can just take this term here equals 0 because it doesn't have any effect on yi. And since xi varies, then the value of 0 should come from beta 1 equals 0. Okay, in this case, we say that xi is not contributing at all in explaining the value of yi. Now, let's see our second scheme. That is, we use this line, the blue line, where the value of yi varies. So, for x equals something between 5 and 10, we can guess the value of y is on this blue line. Okay, so this is the value of yi. Now we change the value of xi. Okay, we get a different value of yi. Okay, although it's not exactly the same, our guessing value is here, not exactly the same as the true value in here, but at least it's close enough. And here, take another value of xi, it will give us another value, a different value of yi. So in this case, here, different value of xi will give different value of yi that is kind of like closer to the actual value of yi. This can happen because in this line, this is a straight line with beta 1 not equal to 0. in that case, we say that xi is contributing in explaining yi through this equation. So what does the illustration tell us? It tells us that to test whether the model is useful or not, we need to test whether the beta 1, the regression slope, equals 0 or not. To test this hypothesis, we need to do some calculation, compare that calculation with something else, measure your mistakes, whether you are making a good decision or not. So then you need to set a rule. So what is that we need to calculate? Now you ask yourself, what is that you are testing? Here we are testing the beta 1, whether it is 0 or not. So it means that you collect your data, your sample data, you do your calculation on that beta 1 based on your sample data. And that's how you get that beta 1 cap. Then, this is the one that you get from your data. This is the one that you want to check. So we need to compare whether the one that you get from data is close enough to the one that you are going to test. Okay, so if they are close enough, let's say beta 1 cap is close enough with beta 1, then we can say that your data supports the null hypothesis, which means that you can conclude that the null hypothesis is the one that is correct. But if the beta 1 cap is not close enough with the beta 1 in here, you can say that your data is not supporting the null hypothesis. In that case, you need to reject the null hypothesis. But then in here, we cannot just say, that the question is that how close is close, how far is far. So we need to measure that. So here we will make use the central limit theorem. Like, we can measure how far is far, how close is close, and then what is the probability of making a mistake by saying that what I'm getting here is close enough to 0. Something like that. We need to measure the probability. We can't just say it's close or it's not close. We just say that it is close with the probability of this and this. It means that we need the distribution. And then we can make use the central limit theorem that's saying that whatever it is, in our case is the beta 1 cap, whatever is the distribution, but if it is corrected by its mean, and the mean here is we take it from the null hypothesis, that is beta 1 equals 0, that's the one that we can test. So then beta 1 cap minus the beta 1 under the null hypothesis divided by the estimated value of the standard deviation, it will follow a t distribution. So then we have a rule. Okay, so we will reject the null hypothesis if this value of beta 1 is far with the value that's given by the null hypothesis. How far is far? Following this rule here, the t distribution here, it is called, the distance is called far if they are on the rejection region. So we say that we will reject the null hypothesis and say that our model is useful if the difference between the estimated value of beta 1 and the beta 1 under the null hypothesis is large enough, and that large enough is measured by this, the value of the t that is at the critical region. So up to now, we learned that the model is useful when the explanatory variable x can explain the target variable y, and then the model's goodness of fit is assessed by testing the slope of the regression line.